For thousands of years, we've only been able to look up. Every star, every galaxy, every piece of the universe we've ever discovered came to us as light. But what if we could listen to it instead? Back in 1916, Albert Einstein proposed that space itself can actually bend and vibrate. He predicted that massive cosmic events would send invisible ripples moving outward through the fabric of the universe, and he called them gravitational waves. Proving that those invisible ripples actually exist is incredibly difficult. It took nearly an entire century of intense engineering before humanity could build a machine sensitive enough to feel space vibrating. Then, in 2015, a machine in the United States called LIGO felt a tiny shudder. Two black holes had crashed into each other over 1 billion light-years away, and the resulting ripple finally washed over Earth. Einstein was right. That single collision shifted the entire trajectory of physics. After millennia of only being able to watch the sky, astronomy transitioned from a silent movie into a talkie. So how do you build an ear for the universe? LIGO isn't a traditional telescope. There are no glass lenses pointing at the sky. Instead, it looks like this, a massive L-shaped concrete tube stretching for 4 kilometers across the landscape. Inside those tubes is a clever trap for catching gravitational waves. A powerful laser is fired into a splitter, sending 2 identical beams of light traveling down 2 perpendicular arms. Those separate laser beams fly down the 4-kilometer tubes, hit perfectly smooth mirrors suspended at the far ends, and bounce right back to where they started. Under normal conditions, both lasers return at the exact same moment. But when a gravitational wave rolls through our planet, it actually stretches one arm of the tube and squeezes the other. The distance changes. And because the physical distance changes, those returning laser beams arrive out of sync. To understand how hard this is to measure, we have to talk about scale. That stretching and squeezing effect alters the length of the 4-kilometer tube by a distance less than 1/10,000th the width of a single proton. Catching a movement that impossibly tiny requires some of the most extreme technology on Earth. The tubes must maintain an ultra-high vacuum, completely stripped of air and particles, and the optics must be completely flawless. The biggest problem with a machine this sensitive is it feels everything else, too. It picks up vibrations from trucks driving on distant highways, from tiny earthquakes, and microscopic jitters of light particles inside the machine. All of that local noise can easily drown out a faint cosmic signal. Because of this interference, a single L-shaped detector operating alone on Earth is essentially blind. It can hear that a collision happened in deep space, but it has almost no way of knowing exactly where that sound came from. To figure out where the waves are coming from, the United States currently operates 2 of these massive LIGO detectors, sitting thousands of miles apart on opposite sides of the country. But 2 machines aren't quite enough. Think about how human hearing works on a crowded street. If you hear a loud crash, having 2 ears helps you guess the general direction, but you often have to turn your head exactly where the sound originated. Pinpointing a signal in deep space requires a third point of reference. Geometric triangulation with just 2 US detectors can only narrow the source down to a massive sweeping arc in the sky. It leaves astronomers with an impossibly large area to search. The solution is adding a third detector to the network, located geographically far away from the first 2. Adding that third point shrinks that massive search area down to a precise, localized pinpoint in space. The solution is Project LIGO India. Approved by the Indian government, this is a 2,600 crore rupee mega science initiative that will be built in the Hingoli district of Maharashtra. The construction is a massive undertaking. The company Larsen & Toubro recently secured the contract to build the highly sensitive civil infrastructure, including the housing for the 8 kilometers of ultra-high vacuum tubes. Bringing a complex and specialized facility like this to life comes with procedural and tendering hurdles, but the project is officially ramping up, with completion targeted for April 2030. Building a facility this precise on domestic soil forces local industries to level up. Manufacturing the complex vacuum systems and the flawless optical components requires Indian high-tech manufacturing to meet the strictest tolerances in the world. The effort to stabilize lasers and isolate the mirrors from ground vibrations will also produce secondary spin-off technologies. The advancements made here will bleed over into improved seismology and highly precise navigation tools. But the biggest impact is on the country's scientific talent. For decades, top researchers wanting to work on the extreme edge of physics often had to move abroad. LIGO India provides a home for that expertise, keeping world-class observation and the brightest minds firmly inside India. For a student sitting in a physics classroom right now, the timing is perfect. By the early 2030s, this giant ear in Maharashtra will be fully awake, and that next generation of scientists could be the ones analyzing its first major cosmic discovery.